In chapter 8, we're going to be dealing with defining integration formulas for basic functions, trigonometric functions, inverse functions, all this other stuff. We're going to look at formulas and deriving all sorts of equations. In your packet that I gave you last week, you have these formulas. All you have to do is get it into one of these forms, and you know what the inverse is. I mean, the inverse with the integral. Of course, this is for indefinite integrals. For definite integrals, you just have bounds we put it in. Let's look at example 1. Here we have a definite integral from 3 to 5. X squared minus 3x plus 1. On top, we have 2x minus 3 dx. So, what procedure would you utilize in this example? Does this bottom fit into any of these right now? No, no, no. Okay, so what we have to do is we have to use substitution. Let's U be what's inside the radical. The question most commonly asked is, which one do you define as U? Remember, we also have to find du. So the longer equation, the more complex equation, will usually be defined as u. What's the derivative of u? Here's u. What's the derivative of this function? 2x minus 3. So this is du dx, because we're taking a derivative with respect to x. Which could also be written du equals 2x minus 3 dx. So we see on the numerator, it's 2x minus 3 dx. So we can put a du up there. And on the bottom, we have the square root of u. Are we done with the transformation? Are these bounds with respect to u or with respect to x? With x. So we have to change these so they refer back to or reflect the u function. So we have to look at what is u, because remember, u is a function of x. So we have to find u of 5 and then u of 3. So 5 squared, 3 times 5 plus 1, 25 minus 15 plus 1. That's 10 plus 1 equals 11. So this bound goes to 11. Now the 3, u of 3 equals 3 squared minus 3 times 3 plus 1. 9 minus 9 plus 1 is 1. So this becomes 1. So my new bound for my substitution is from 1 to 11. Why is that important? Did we have to change these bounds of integration? The answer is no, because we could have used the substitution method to find the integral and then go from there, put it back into x functions of x. And we could have kept it at 3 and 5. Or if we change it to the u function, we can keep it there as long as we change the bounds of integration. Now all we have to do is simplify this and plug these in for u. And we'll get the same answer. Okay, so what's the integral of this one? So I set it up from 1 to 11. U to the negative 1/2 du. Because remember, the square root is the 1/2 power. It's a square there. So what's the integral? We take and add 1 to that one. So negative 1/2 plus 1 is positive 1/2. And then we divide by it with what we added. So now our bounds go from 1 to 11. So this 1/2 becomes 2. U to the power 1/2 from 1 to 11. Which is the same thing as 2 square root of u from 1 to 11. So we have the square root of 11 minus the square root of 1, which is 2 square root of 11 minus 1, whatever that is. So it'll be between 4 and 5 because square root of 11 is between the square root of 9 and square root of 16. So it's 3 point something. Minus 1 is 2 point something. 2 times 2 point something is 4 point something. Four point 4.6. At the end of the class today, I also put all the sheets, all the integral stuff that we have from the last chapter. I'll put them on one page, so we'll get it at the end of class. What? Let's look at example 2. Sometimes we need to complete the square. We have to use some algebra technique to simplify our equation. So you complete the square to evaluate our function to the indefinite integral. Because we can't do anything with this just yet. It doesn't match anything we have. So if we complete the square, what's completing the square going to do for us? It'll put us into an equation where it's a perfect square. And then we'll take the square root of it, it gets rid of the square root. So in this case, since we have a binomial as order degree 2, that means we can complete the square. How many of y'all remember how to complete the square? Okay, so let's look at this thing. We take the term we want to complete. We have 8x minus x squared. What's that graph going to look like right now, the way it is? What kind of graph is it? It's a parabola, but the leading term is negative, so it opens down. The rule for completing the square is your leading coefficient has to be 1, positive 1. So what we have to do here is we have to factor out a negative. We have to get rid of that negative sign. So that gives us this equation. Now, completing the square, we have, remember, our quadratic equation is A, B, C. What you have to do now, we have to take B over 2 squared. And since we add it on the inside of this thing to complete it, we have to subtract it from the outside. Because whatever we add, forget this parenthesis here. Whatever we add here, we have to cancel it also. Because we can't change the equation, we're just changing the way it looks. So since I added B over 2 squared, I also have to subtract B over 2 squared. Okay, I'll forget this thing that exists there. Think about if we had ax plus b squared, which is ax plus b. And if we multiply these out together, we get a squared, x squared, abx, abx. We have 2 abx plus b squared. So whatever this is, when we put it over here, it's got to be half of that because it's doubled. So if this was 8, this would have to be 4 because we have to multiply by 2. So that's why we divide by 2. No problem. You're welcome. So what is B? B is what's in front of X. It's 8. So we have X squared plus 8X plus 8/2 squared minus 8/2 squared. X squared plus 8X. Now, inside the parentheses, only do what's inside the parentheses. Do not work them out just yet. Only work what's inside the parentheses. Don't square them. Because you notice we have to have our first and last term squared. So now I can separate these. So I have X squared plus 8X plus 4 squared. And this negative goes here, so it becomes a plus 4 squared. Now this is a complete perfect square. We take whatever is under the squares and the first sign. Bless you. So it's X plus 4, and that's squared. Plus 16. Oh, here's the original equation. I somehow put a negative there. So that's got to be negative. That's got to be negative. That's plus. That's negative. So it's X minus 4 plus 16. I don't know where I got the negative in front of the 8. I'm sorry. So to make this thing match one of these things, we have to have the A in front on most of these. See, on the square, we have A squared minus X squared. There's no coefficient there, or is there? So we can rewrite this to be 16 minus X minus 4 squared. So now we have dx over 8x minus x squared. That becomes now we have we've completed the square. We have 16 minus x minus 4 squared. So which one of these does it look like? Can it be this one? No, because there's no x in front. Can it be this one? Possibly. Can it be this one? Possibly. Can it be this one? What's the difference between these three? Right, this one's a squared minus x, so the negative's in front of the x. This one's x squared minus a, so the negative in front of the a. This one's a squared plus x squared. They're both positive. Do we have that here? Remember, a represents the number. So what we have here is the square root of 4 squared minus u squared. Because remember, u is a function of x, so that's the u. This is a number, and we have to make them into squares. 16 is 4 squared. So which one matches? No, this is a squared minus u squared. Look at your chart. Which one matches a squared minus u squared? What's that? The inverse of sine, right? It's the inverse of sine, so it's the answer is sine inverse of x over a, or in this case, u over a. What's u? X minus 4. What's a? 4 plus c. There's your answer. Again, it's the algebra part that's going to be difficult. The last time you guys completed a square was probably in algebra. Want me to do another example of us complete the square? Okay, let's just do an algebra complete the square example, and I'll write down the procedures. Remember, we have our equations are in this form. They have to be equal to 0. We could have done the last one like this, but this is the general step. Okay, first off, here are your steps. First, a must equal 1. If not, then divide each term by a. So is our a 1? No, it's what? 2. So we have to divide each term by 2. We will multiply this term, or this value, back into the equation at the end. So now we have x squared minus 3x plus 3/2 equals 0. Because what's happening here, this is the same as if we factored out the 2. It's still going to be a coefficient. It's just not there. So we'll multiply it in at the very end. Next step. Move all non-x terms to the other side. So we got to move that over there. How? By subtracting 3/2. Third step. Add b/2 squared to both sides. So we have x squared minus 3x plus 3/2 squared. Negative 3/2 plus 3/2 squared. On the left side, only do inside the parentheses. Don't square it. The right side, work it out completely. Okay, we can't do anything inside the parentheses over here. Can't simplify further. But on the other side, 3/2 squared becomes 9/4. We distribute that square to both top and bottom. In order to combine those two on the right-hand side, I have to get a common denominator. So I got to multiply this one by 2/2. So we got -6 plus 9/4. Which is 3/4. This is where we complete the square. On the left side, inside a parenthesis, put the first term, whatever's under the square, first term, first sign, and then third term. and then put in parentheses and squared. So it's only whatever's under this, the squares. So it's x minus 3/2 squared equals 3/4. Now, move this to the other side. We got x minus 3/2 squared minus 3/4 equals 0. That's what I said. Because you're completing the square. If you took these two and multiply them together, you'd come up with that. So we're making it smaller when we're completing the square. And remember, we had to put the 2 back in there that we factored out, that we divided out earlier. And there we have it. That's completing the square. Ideally, what we do, well, the reason we would complete the square in algebra is to solve for a variable. In other words, we would move everything to one side, solve for x. But in this case, what we're trying to do is trying to get the x by itself on one side. I mean, getting the equation to one side, so we put it, see if it fits any of our formulas. And in this case, no, it doesn't. So that's how you do complete the square. And I'm pretty sure the homeworks and the assignments are going to be nice enough to, so you don't have any fractions or coefficients of A. Let's look at trigonometric ones. So we have to use trigonometric identities or equivalent expressions. What if we had cosine of x times sine of 2x plus sine of x cosine 2x dx? So what's the trig identity here, or trig, the equivalent trig statement for this? You have cosine x sine y plus sine x cosine y. What that becomes is sine x plus y. This is the identity we'll be using for this one. If you had sine, sine, cosine, cosine, then it'd be the cosine x minus y. But again, these are all equivalent statements that we use from the trigonometric identity table. So in our case, since we have cosine, sine, sine, cosine, it becomes sine. The first one's the x. The second one's the y. We can combine like terms. Since we have a chain rule here. So we're saying that our u value is 3x. So we have to find the du dx, which is what? 3. Or another way of saying this is du is 3 times dx. Do we have a 3 dx inside here anywhere? No, so we got to put one there, which means we got to put a 1/3 out in front. So this becomes inverse of sine u du. Because we placed that 3 there, because du has to be 3 dx. So we have to cancel out that 3. What's the integral of sine? Negative cosine. Because remember the unit circle. Sine is up here. Integration goes this way. So it goes negative sine and cosine. So it goes this way. These are the integrals. So it's negative cosine u plus c, which makes it negative 1/3 cosine 3x plus c. And there's your answer. Make sense? Do what? With this? Or that? With c? No, the c, if you multiply c by 1/3, it's just another c. It's a constant. Because remember, why is that not important? Is because when we take a derivative, it disappears. And yeah, so we don't know what the value of c is because we weren't given an initial condition. We have to have an initial condition to see exactly where that c would be. Well, we plug it into the equation and then we can find out what the integral is supposed to be, and that'll tell us what c is supposed to be. We'll get to those. So let's look at this one. We have a definite integral from 0 to pi over 4 of dx 1 minus sine x. Here we have a couple of things we can try. One, is this an identity? What would the identity be? It is cosine squared plus sine squared equals 1, but that's not squared. So we can't use that. There are no identities for this. So if we plugged in 0 there, that's 0. If we pi over 4, but again, we can't really do that because we first take the integral of it. Makes it easier for us. There's a second method we can do. Since we can't find identity, what do we do in Cal 1 whenever we had a square root? An equation that looks something like this: square root of x minus 100 minus 10. If we had a fraction like this, these have to stay together because it's the square root that's the problem, not the inverse. It's called something else. You're very close. Because of this is one that's giving us trouble. If we multiply top and bottom by its conjugate, in other words, the conjugate is change the sign between them. And then what that's going to do, it's going to get rid of the radical on top and give us one that's possible on the bottom. So what we have to do here in this case is multiply the top and bottom by the conjugate, which is what? It's a plus sign, right? So it's 1 plus sine x, 1 plus sine x. Let me put the dx back here so it's always at the end. So when we multiply these out, what do we get? We get 1 plus sine x. And what do we get on the bottom? 1 times 1 is 1 plus sine x minus sine x minus sine squared x dx. You have to FOIL them out. So the sine x cancel. One plus sine x. And on the bottom, we have 1 minus sine squared x dx. Now do we have an identity? Now this 1 minus sine squared becomes cosine squared. We have 1 plus sine x over cosine squared x dx. What do you think next thing is to do? The derivative of cosine squared is not 1 plus sine, so we can't do that. We have a monomial on the bottom. So we can make it a lot easier for us if we split them up. 1 over cosine squared is? What's that? I need somebody with confidence to say it out loud. 1 over cosine. It's secant squared, right? Secant squared. You have to say it out louder if you're confident. Now, what do we do with this one? This one becomes sine x over cosine x times 1 over cosine x. Since we have 2 cosines on the bottom, we can take 2 of them. What is sine x over cosine x? Tangent times 1 over cosine. You're in Cal 2, guys. This should be second nature to you. So what's the now, because we have the sum rule, we can take both of these separately. We can take the integral of 0 pi over 4 secant squared x plus tangent x, this is pi over 4, secant x dx. So what's the integral of secant squared x? Use the sheets I gave you. It's back on the first page. Where do we see secant squared? What does it become? The integral of secant squared becomes? Tangent. It's number 8 on your sheet. So it's tangent x from 0 to pi over 4. Now the integral of tangent secant. What's the integral of tangent secant? What's that? Secant. It's number 10. Again, I need you guys to do this. If you have the packet for chapter 8, it's behind the first page. So we have, in the first one, we have tangent pi over 4 minus tangent 0 plus secant pi over 4 minus secant 0. So what's the tangent of pi over 4? Don't use your calculator. You should know this by heart, or look at draw a chart. What is the value at pi over 4? 1, because sine and cosine are both the same at pi over 4. So this is 1. What's the tangent at 0? Yeah, because sine over cosine. Sine of 0 is 0, cosine is 1. Secant pi over 4. Tell me the final answer, not equation. Simplify it all the way out. You cannot have a radical on the bottom. Square root of 2. For those of you who don't know, secant is equal to 1 over cosine. At pi over 4, cosine is square root of 2 over 2, which becomes 2 over square root of 2. You can't have a radical on the bottom, so you multiply top and bottom by square root of 2. So we have 2 radical 2 over 2, square root of 2. Secant of 0. One. Cosine at 0 is 1. Secant is 1 over cosine, which is 1 over 1. So I don't need the parentheses. One negative 1 cancel, 0 is gone. So the answer is radical 2. All right, let's look at the next type of example. Example 5. The indefinite integral of 3x squared minus 7x over 3x plus 2 dx. What do we notice about this structure of this equation? There are more x's on top. The higher degrees in the numerator. Up until now, that should be on the bottom, or the radical is on the bottom. So let's do division. This is an equation. That's an equation. So what kind of division can we do here? How many of y'all remember long division? So if we had 9 over 4, that can be written as this. 4 goes into 9 twice. 2 times 4 is 8. Subtract them, change the sign. And there's your remainder. So the answer is 2 and 1 over 4. That's what we're going to try to do, which this becomes 2 plus 1 over 4. So you see now, if we can do this with this equation, these are easy to integrate. Those are just do the straight integration. These are what we have the chart for. So let's look at this example. We have 3x plus 2 goes into 3x squared minus 7x. How many times? So look at the first terms. What times 3x gives me 3x squared? X. So now I multiply. X times 3x is 3x squared. X times 2 is positive 2x. Change the sign. Because we're subtracting them, change the signs. And now add. The first term should always cancel. So now we have negative 9x. Can we go any further? Yeah, look at the first terms. Does 3x go into 9x? 3 goes into 9 3 times, but it's got to be negative, so it's negative 3. So negative 3 times 3 is negative 9x. Negative 3 times 2 is negative 6. Change the signs and add. This is your remainder. Everybody okay so far? So our equation can be rewritten as x minus 3 plus 6 over 3x plus 2 dx. This indefinite integral. So we can do each one of these separately. So what's the integral of x? Yeah. Add 1 to the exponent, which is 2, and divide by 2. Integral of 3, 3x. Now we have a problem in this third one. Because if we look at this one, do we have du over u? If this is u, what's du? 3. How do we get from 3 to 6? We have to multiply by 2, which means I got to put a 1/2 out in front. So it's plus 1/2 du over u. What's the integral of du over u? The integral of du over u. Ln absolute value of u. Of course, now it's plus c since it's an indefinite integral. What is u? U is 3x plus 2. And there's your integral. So we took a rational equation that looked pretty consolidated, and we spread them out to things that are easy first, and then we have to worry about the last one at the end. Let's look at example 6. We have indefinite integral of 3x plus 2 over square root of 1 minus x squared dx. So what would you do here? We can't do long division because we have a radical on the bottom. Is this is u, is that du? No, because if this is u, du would be negative 2x. That's not at. So let's separate them, see if we can do anything individually. So we have 3x over square root of 1 minus x squared dx plus integral of 2 over 1 minus x squared dx. The 3 and the 2 are both constants. They could be taken out in front. Now we can go back and check again. Can we do the u du thing? What is u? Or what would u be? One minus x squared. So du would be negative 2x dx. Because take the derivative of this one. So does this one at least work with this one? What's missing? We need to put a negative 2 there, which means we have to divide by negative 2. What about this one? Okay, so this first one we have simplified. It's negative 3 over 2. The integral of du over square root of u. And what happens to this next one? But let's complete this first one. Let's do this side first. So we have negative 3/2. This radical goes up on top, becomes u to the power negative 1/2. The integral of this one would be u to the power 1/2 over 1/2. The twos cancel. Which is -3. U is 1 minus x squared. So that's this part. What about this other side? What's the integral of 1 over radical 1 minus x squared? Does it match any of our formulas here? So we have 1. Inside here, we have 1 minus x squared. This is our a. It's actually 1 squared minus, so a is 1, u is x. So do we have anything that says a squared minus u squared in the square root on the bottom? The only one that says a squared minus u squared in a square root on the bottom is number which one? 18. So it becomes the inverse sine of x over a. So this one becomes the inverse sine of x over a plus c. So the inverse of sine x is x, a is 1. So it's inverse sine of x plus c. And that's our answer. Oops. It's a -3. All right. Example 7. Now, because so far the first 6 examples had a specific reason we can do. This example follows the logic of do what you have to. If that doesn't work, try another thing. Because there is no set rule on this one. We can't divide it, we can't do long division. We can't split it up. Is this rule anywhere in our chart? No, we don't have any cube rules. So what do you think we should do? Another method we have is substitution. Can we use substitution? Well, let's try. Let that be u. What's du? So derivative of 1 is 0. What's the derivative of x squared? Square root of x. Dx. So how does this gonna go back to this? We now have d. Let me put this over here first. So I don't touch that. So what's dx? On this, we have u cubed on the bottom. What do we put on top? We don't have du. We have a dx. So only place we have a dx is here. Can we solve for dx? The answer is yes, always. We can solve for everything. So what is dx going to equal? So dx, we can substitute 2 radical x du. Now what we do? What can we do now? What is the square root of x? Because this is what we're trying to do. We're trying to get away from x. We're trying to go to u. So we took dx, we solved for dx, we got 2 radical x du. We still have an x value here. What is radical x equal? Is there anything we can do over here for radical x? All right, here is radical. So radical x equals u minus 1 from this equation. So we have 2 radical x is u minus 1 du over u cubed. Now we're getting closer. We can either distribute that or factor it out, that constant on top. Let's go ahead and, well, because it's going to change with that one. So let's go ahead and distribute. So we have square root of 2u minus 2 over u cubed du. How does that help us? Well, we now have a monomial on the bottom and an equation up on top. Because now what we can do so what does that give us? The u cancels, giving us 2 over u squared minus 2 over u cubed dx. How do we combine these together now? Or actually, do we need to? This should be du, I'm sorry, not dx. What we have here is 2 integral of u to the power -2 minus 2 integral of u to the power -3. These are both du. The integral of u to the power -2 becomes u to the power -1 over -1. U to the power -2 over -2. So this one makes it a -2, 1 over u. The negatives cancel, the 2's cancel. So we have 1 over u squared. Plus c. So that becomes -2 over u plus 1 over u squared plus c. Put these together, how? Combine like terms, what do you need? That's u squared, that's u, so I need a u over u. So I have -2u plus 1 over u squared. Remember what u equals? U equals 1 plus radical x. That's what's inside the radical. Let's put the leading term as 1 minus 2, 1 plus radical u over 1 plus radical u squared. Radical x, 1 plus radical x squared on the bottom. This becomes 1 minus 2 radical x. Now I'm just cleaning it up. 1 minus 2 is -1 minus 2 radical x 1 plus radical x squared plus c. So again, was that easy? No. Was it long? Yeah. So you just pick a place, pick a direction and go. If we can't use one of the ones we used previously because nothing would work. We can't use the table. We can't use the du over u. So let's try something else, something algebraic. All right. So we have evaluate this one. Negative pi over 2 over pi over to pi over 2 x cubed cosine x dx. So what can you see about this function? What method? Well, do we have anything that does with the product rule? Integration of product rule? Not yet. So how do we solve this one? Here's the clue right here. It's saying from negative pi over 2 to pi over 2. There's a property that we discussed in calculus 1 that says this. Or I could even, instead of that one, I could use the half circle we want to use already. If the function is even, if it's an even function, that means the negative side and the positive side are going to be equal. And we could, it's going to be 2 times this one side. That's the area. But this is if the function is even. If it's odd, that means the area of one side and the area of the other side. So it's positive area. That's this side. This is negative area. We'll give you a 0. Because if it's an even function, they're both going to be positive or they're both going to be negative. It'll give you twice whatever the area is. So twice this area is our answer. Why is that important? Because look at these two functions. This is f of x, and this is g of x. What do you know about f of x? Is it odd or even? It's odd because the degree is odd, which means that if I take equidistance on the interval of integration, domain of integration, then they're going to cancel each other out. So this area is 0. Cosine is what? Odd or even? It's even because at 0, it's 1. At pi over 2, it's 0. And pi over 2 is 0. Since this area from negative pi over 2 is 0 times, so odd times even is odd. Think of negative times positive is negative. So therefore, your integration answer will be the answer of the odd function. So what is the integration of the odd function from negative pi over 2 to pi over 2? 0. Sometimes we can just look at the functions and determine what is going to happen. Because x to the cubed is an odd function, cosine's an even function, so the answer is going to be the odd function result. And from negative pi over 2 to 0, it's negative area. And from 0 to pi over 2, it's positive area. So they're going to wash out. So this whole area is 0. That's how it works. What's that? Is sine odd? Let's see. Sine's here. Yep, because from negative pi over 2 to pi over 2, it's odd. Because one side's negative, one side's positive. Same thing, be 0. Because the sine function would be negative area here, it would go to 0. The same thing. So if you have an odd function and an even function, you do the integration of the odd function, that's going to be your result. And this is brought about by theorem 8. Let f be continuous on the symmetric interval negative a to a. If the function is even, then that means it's going to be twice the distance from 0 to a. Because they're going to be equal both sides. If it's odd, from negative a to a, from negative a to 0 is negative. From 0 to a, it's positive, same values, and they become 0. So that's what it looks like. If it's an even function, we just add the two together, or it's twice one side. If it's an odd function, then from negative a to a, they cancel each other out, become 0. And that's all she wrote. You should have it in there. It's on the last page of chapter 8, section 1. I didn't put it in there? No. You don't have theorem 8? Okay, let's write this one down then. Because this is a very important one that's going to save a lot of time for you. Theorem 8 says that f be a continuous function on a symmetric interval. This is important. It's got to be continuous because there can't be any jumps. And it's got to be a symmetric interval. Negative a to a. If f is even, then the integral from negative a to a, f of x dx, is twice the integral from 0 to a. Why is it from 0 to a? Because it's symmetric. It's going to be the same on both sides of the y-axis. So it's twice 0 to a. If f is odd, then we go from negative a to a, and it becomes 0. Which what you're gonna look at is this way. So from negative a to 0 of our function is negative area. And then from 0 to a of our function is a positive area. So a minus a equals 0. That's what it's telling us. So the definite integral of symmetric functions looks like this. So that's what it's telling us. It's gonna be the same thing, because even if it shifts from left to right, if we have an interval where it's symmetric, then, well, actually, no, take it back. If we shift it to the left or right, is it gonna be, let me go back to that question. If we shift it, let's say we had an odd function, and instead of here, we shift it from A to B. If we shift the whole thing, as long as it's in the same period, then yeah. Because the bottom part, this part is still gonna be below there. This part's still gonna be above there. Because if you shift the entire equation, then that's all you're doing. Whenever you do a transformation in math, you're actually changing where the origin is. You're moving it horizontally or vertically, and then the graph from there either constricts or stretches. Otherwise than that, it's gonna be the same thing. If the answer is gonna be negative, it's gonna be negative between A and C. Between C and B, it'll be positive. But okay, now, as if we translate or transform all of our functions left or right, or that's not up and down, it has to be left and right. If it's up and down, here's A and here's B, and let's say I shifted it up. Now the areas are all positive. Yeah, because if it's left and right, we'll have some parts that are negative, some parts that are positive. But if it's shifted up, all parts are positive, or shifted up, all parts are negative. So that's why when it comes to transformations, this doesn't work. This one has to be continuous function on a symmetric interval. Whatever the interval is, it's got to be symmetric. That was a good question, actually. Yes, thank you. But no, yeah, if that's the case, then again, that's why it's near the part that says trial and error. See what happens.